Today we are going to discuss a topic of detection of radar signal in a noise. So detection of radar signal is in noise. So here if you what are the methods how we are going to be taking the original signal in the noise. So here we are using the method is matched filters, correlation function, definition of non-matched filters, efficiency of non-matched filters, matched filters of non-white noise. So radar receivers, here only we are getting the problem to receive the original signal. So in the radar receivers we are going to learn about radar receivers, how we have to construct the radar receivers, what is the characteristics of the radar receivers, what are the requirements of the radar receivers, and receiver noise figure, radar displays, deflection modulation, intensity modulation, and what types of duplexers we have to use, branch type, balance type, circulator has duplexer. So here first we have to use the phased array antennas. Define phased array antennas, radiation pattern of a phased array antennas, beam steering and beam width changes. So here what are the methods of beam steering is parallel feed arrays, series fed arrays, series versus parallel feeds, applications and limitations of the this. Now we are going to see the detection of radar signal in noise. The two basic operations performed by the radars are detection of presence of reflection object, extraction of information from the received waveform to obtain the target data such as a position, velocity and size. No noise limits the capability of any receiver. So what is the basic operations of the radar? First one, it is have to detect the information of the presence of reflection object, extraction of information from the received waveform to obtain target data such as position, velocity and size. Next one, noise limits the capability of receiver. So here, to minimize the output peak signal to the noise power ratio of a radar improves the detectability of the target. A linear network program, this is called matched filter. Matched filter, a network whose frequency response function maximizes the output peak signal to mean noise power ratio is called matched filter. If the bandwidth of the receiver passband is wide compared to the occupied signal, energy noise is introduced in the excess bandwidth, which lowers the output signal to noise ratio. On other hand, if the receiver bandwidth is narrow than the bandwidth occupied by the signal, the noise energy is reduced along with considerable part of the signal energy. The net result is again lower the signal to noise ratio. The rule in pulse radar is that the receiver bandwidth should be approximately equal to the reciprocal of pulse width. The bandwidth of the RF and mixer stages of the super heterodyne receiver is usually large compared to the IF bandwidth. The matched filter is located in the IF stage of super heterodyne receiver. Therefore, maximum signal to noise ratio at the output of the IF amplifier. So, now matched filter frequency response function. So matched filter minimize the output peak signal to noise ratio when the input noise spectrum density is uniform. The frequency response function of the matched filter is given by h of f is equals to ZA into S conjugate f of e power minus j25f Tm, where Ga is the constant and Tm is the time at which output of the matched filter is maximum. So S of f is complex conjugate of the spectrum of input signal S of t. So next, the Fourier transform of the received signal S of t is equals to integral minus infinity to infinity S of t e power j 2 pi f of t. The received signal spectrum is now is magnitude of S of f into e power j power si of S of f. So where S of f is a amplitude spectrum and psi S of f is a phase spectrum. So the matched filter frequency response function in terms of amplitude and phase is expressed in below here. So the frequency response function of the matched filter is the conjugate of the spectrum of the received waveform except for the phase shift of e power minus j 2 pi f Tm. The phase shift varies uniformly with frequency. It affects to the constant time delay. A time delay is necessary in the specification of the filter because the physical reliability, since there can be no output from the filter until the input. So now what we are going to do is, let GA is equals to 1. Then h of f e power minus j sin m f of f is equals to s of f e power j psi s of f minus 2 pi f dm. Equating amplitudes and phase in the above expression, h of f is equals to s of f. Phi m f is equals to minus phi s f plus 2 pi f m tm. Above expression indicates that the magnitude of matched filter frequency response function is same as the amplitude spectrum of the input signal. Phase of the matched filter frequency is negative for phase spectrum of the signal plus phase shift proportionality to the frequency. So, matched filter is also described by its impulse response h of t. Impulse response is inverse Fourier transform of the frequency response function h of f and is given by h of t is equals to integral minus infinity to infinity h of f e power j 2 pi f of t df. So, substituting equation 1 in equation 8. So, by that h of t is equals to g of a integral minus infinity to infinity x conjugate of f into e power minus j 2 pi f tm by t. Since x conjugate is equals to x conjugate of f is equals to s of minus f. So, therefore, h of t is equals to ga integral minus infinity to infinity s of f e power j 2 pi f tm by t into df. So, h of t is equals to ga into s minus t. This equation shows impulse response of the matched filter is the time inverse of the received signal. The received signal is revised in time, that is starting from fixed time tm. So, the received signal s of t and its impulse response h of t of the matched filter is shown in below figure. So, s of t and h of t. So, after that